All right, cool. So let's jump into transformations. Now, transformations is a pretty simple concept, I think, because like I said, if you can do one, you can do all, right? What's the notation that you guys use in class? Remember how we use like AKDC? Is it the same, or what letters does your teacher use?
Um, it was the same last year, but we haven't started the union yet, so I'm not sure what we use.
Okay, cool. So it doesn't really matter, right? So at this level, we're gonna write, instead of writing y equals, right, we're gonna write f of x equals. We're gonna do the function notation. Ultimately, they both mean the same thing. So f of x, this is a replacement for y. Now, in a transformation, it's always going to take this form. A times, A is always gonna be outside, and then you have your function f. And then you have k x minus d plus c. So in here you have A, which is the vertical stretch factor, right? What's K? K is the horizontal stretch factor. But K is the opposite. We're going to talk a bit more about that in a bit. Anything inside the function is opposite. D is also inside the function. Notice how inside of f you have k and d. Anything inside of the function affects it horizontally. It affects it in the x direction. So d, it's going to be a horizontal translation. We call it translation, but it's a shift. The technical word is a translation. It means it goes left or right. C is a vertical translation. It goes up and down. Yeah, you remember this?
Mm-hmm.
So once you have this, everything is going to be in this form. What we do is that we used something called the point mapping rule. So you're going to have an f. This is going to be your parent function. What we do with this is that you make a table of x, y with just the parent function, just for this f. And then you make a table of x and y for the transform function, and this next formula is very important. X always becomes, this is the point mapping rule, X always becomes X over K plus D. Y always becomes AY plus C. Then you're gonna have these points because this is just from the parent function. You can come up with these on the fly. And then we plug these numbers in here as x and y to get a few points. Usually, I think if you have 5 points, this is the maximum I've seen. If you have 5 points, you're good to go. And then the last step is just to plot those 5 points and see what it looks like compared to the original function. Okay? So that's basically transformations. But what we're gonna do is we're gonna do a bunch of practice problems. We're just gonna hammer this thing home. Um, so let me find a nice example. All right, let's start with this one. Okay, what's the parent function here? What's f? It is root x. You see here?
Mm-hmm.
So your parent function is root x. What we're gonna do is we're gonna sketch this transformed function. I'm gonna give you the steps, okay? Step number one, anytime you're trying to sketch a transformations, write down your AKDC. And these, it can be a bit tricky, especially K and D can be a bit tricky, but A and C is literally how you see it. So again, remember your general function f of x was a. So here a is going to be minus 2 times f. K is going to be 3. X minus d is going to be negative 1. Plus c, so c is going to be 4. So let's write those down. A is minus 2. K is 3. What's d?
-1.
Yeah, and c is pretty easy. C and a are the easiest. You just write down what you see. Okay, so now we have our AKDCs. Okay, what does a of minus 2, what does that do to our function? So a of minus 2, it does two things. The minus, right? The negative, it's
Is a
a
reflection.
on which axis, x or y? It's a reflection on the x-axis. Think about it this way, right? A does vertical transformations. So you have a quadratic like this, you make it a negative. Negative x squared looks like this, right? So it's a reflection on the x-axis. This, you're using this plane as a mirror. So that minus sign there does a reflection on the x-axis. It turns upside down. What does the 2 do?
The vertical stretch.
Yeah, it's a vertical stretch. Okay, what does k of minus 3 do? Sorry, k of positive 3. What does that 3 do?
It's a horizontal stretch.
It's a stretch? No, it's not. K is the opposite. So k of 3 is actually a horizontal compression by a factor of 1/3. So if you have a function like this, k of 3 is going to make it much thinner. It's going to flatten it out horizontally, okay? It's the opposite.
It was like itself, it was just 1/3.
Then it will be a horizontal stretch. So if you had this k, so let's say your k was 1/3, then it would look like this. It would just become fatter in the x direction. Okay, k is the opposite. What does d of minus 1 do?
It's a translation.
Yeah, left, right, up, down.
Left.
Yeah. So this is left 1, very simple. The other one is down 4, very simple. Translations are pretty easy. So now what we're going to do is we're going to sketch this transform function. We're not going to dilly-dally. The easiest way to do this is using point mapping rule. You could do it differently. Let me show you how you could do it differently. We're never going to do it that way. I'll just show you how the book likes to do it sometimes. So what they do is they're using the point mapping rule, but they're using only one transformation at a time. So here they're not using any of the translations. And here they use translations. What you can do is instead of using two tables, you can just use one table and you'll get the same exact sketch. So here's the point mapping rule. X, Y on the parent function. In this case, our parent function is the root function. It's going to look like this. Starts at 0, 0. What are some XY points for this curve? So remember, this is your function, right? Y equals 2 root x. What are some other points we can use?
Mhm.
You can use 1, 1. You can use 4, 2, 9, 3, 16, 4. Yeah? And then what we're going to do is we're just going to use the point mapping rule to come up with a new table. And it looks like this. This is the point mapping rule. X over K plus D. And then on the other side, we have AY plus C. By the way, okay, this next part is important. This point mapping formula is only valid if your function is in this form. Here's what I mean by this. let's say you're given this y is equals to 3 root 9x minus 27. Something like this. What's your d value here? Remember, d is the horizontal translation. For this exam, it's 27, it's not 27. Try again. What's your d value? It's actually 3, right? Why? That's because notice in the general form, your k is pulled out of the bracket, right? See this? Whereas here, your k is thrown inside of the bracket. So your d is not 27. That's a very common mistake. To see your d, what you need to do is you need to pull out the k value. So now if you pull out the 9, x minus d, so you see your d value is actually 3. So to use this point mapping rule formula thing, just be careful that your equation, your f of x, is in the right form. The right form just means, usually that's the only thing, your d value might not be accurate. Everything else works out, but your d value might not be accurate. So just make sure it's in that right form. Okay, so that's our formula. So what we're going to do is we're just going to plug the numbers in. So x over k, so x over 3 plus d, so minus 1, and ay plus c, so that's, what's our a value? Negative 2y minus 4, right? Like that. So from here, what we're going to do is we're going to plug this value of 0 in here as x. So look at this. 0 over 3 is a 0. Minus 1 is minus 1. And we're going to plug this 0 in here as y. So negative 2 times 0 is 0. Minus 4 is minus 4. So there you go. That's our first point. And then we rinse and repeat. Next, we're going to plug this 1 in here. So 1 over 3 minus 1 is negative 2/3. We're going to plug that 1 in there. Negative 6. 4/3 minus 1, that's 1/3. I'm now just plugging in all the values in there. 2 in there, negative 8 minus 4, negative 8. And then you can see the general pattern. And for the final step, we are just gonna make a sketch of the original function. So 0, 0, 1, 1, 2, 3, 4, 2. So this is the original function root x. Now our transform function starts at -1 and -4. So -1, 2, 3, 4 starts here. Negative 2/3, negative 6. So it goes down this way. And there we go. We're done with this question. Did that make sense? So transformations, the steps, make sure it's in the right format to see your AKDC. Once you have your AKDC, it's just a matter of creating 2 tables. The first table is just the parent function. The next table is the point mapping rule. Once you have this, it's pretty simple from there. That made sense, yeah? Is this difficult? No, it's not. Okay, let's do one more. But now we're gonna talk about what happens. Okay, so what's the parent function here?
Is x.
It's 2 power x. It's an exponential function. Remember what an exponential function looks like? Looks like this, the parent function, yeah, the parent function. 2 power x. It's gonna start here, an exponential growth, like that. Always goes through the y-intercept of 1. And for every exponential function, the d value, not the d value, sorry, the c value, the vertical translation number, that's always the asymptote. So for example, if you're like 2 to the x minus 3, how do I sketch this? The minus 3 is going to be your asymptote. And what does 2 to the power x look like? It looks like this. It'll look like this. This number, that's your d value. I don't know why I keep saying a d, I'm sorry. It's not the d value, it's the c value. AKDC, it's this value. The vertical translation, it's always the asymptote for exponential functions. That's why 2 power x, the parent function, there's a plus 0 attached to it. That's why there's an asymptote here. So that's what it looks like. By the way, what's the inverse of an exponential function? The inverse of an exponential function is the log function. Looks like this. Well, you know what it looks like. It's a reflection. Inverse function is simply a reflection on the y equals x axis. So if you take this point, it's going to shift here. If you take your asymptote, that now becomes your vertical asymptote. So the inverse of an exponential function is a log function. Looks like this. So this is the inverse of 2 power x. It's log base 2 of x. So anyways, let's go back to this question. We have an exponential function and then we have some transformations, all right? Step number 1, list your AKDC values. What's AKDC here?
A is -2,
Mm-hmm.
K is 3, D is 1, C is 4.
Yes. What does a minus 2 do to the function?
It's a reflection on the x-axis.
Yeah, anything else?
The vertical stretch.
Okay, what does 3 do?
It's a compression.
Yeah. The other ones are pretty simple. So it's a compression by 1/3. Just flip it upside down. If k was 2/3, that would be a horizontal stretch by a factor of 3/2. Okay, like that. D equals 1, it's easy. It's just gonna shift it right 1 units. C is 4, it's just gonna shift up 4 units. So this part is very simple. So now we have our AKDC, so we can just go and build our table. So our parent function is 2 power x. What are some points on the curve 2 power x? Let's see. I'm going to start with this one, -1. What's 2 power -1? Is it -2? So what is 2 power -1 then? It is 1/2, right? 2 power -1. Remember exponents? If you have a negative exponent, you just throw it in the denominator, becomes positive. 2 power -1 is 0.5 or 1/2. What about 2 power 0? What's 2 power 0?
It's 1.
It's 1. 2 power 1 is a 2. 2 power 2 is a 4. 2 power 3 is an 8. So there we go. We have 5 points. Again, this depends from like teacher to teacher. Someone might tell you 3 points. Someone might tell you 5 points. So now you have a table of the parent function. What we need to do next is come up with a table for the point mapping rule. And the formula for point mapping rule is again x over k plus d, ay plus c. So that one here, it's going to become x over 3 plus 1 and then ay, negative 2y plus 4, like that. So now let me just do these. 2/3, 1, 4/3, 5/3, 2. On this side, negative 1 plus 4, 3, 2, 0, negative 4, negative 8. Again, these obviously you can also plug it in a calculator. All I've done here is plug in these x values as x in here. Same thing with the y's. Plugged in these y values as y in here. Now we have everything. Let's just sketch this. So I'm just going to make a rough sketch here. Don't have to be super precise. So exponential function is going to come from here. It's going to go through the y-intercept of 1. And then 2 power 1 is 2. 2 power 2 is 4. So it looks something like this. This is just 2 power x. Now our transform function, what's a good point for our transform function? We have 1 and 2. I guess let's use that. 1 and 2. Notice how that point is unchanged. It's not the same point, but it's just that point happened to be on both curves. That point actually comes from 0, 1. Okay, next one, 4/3 is 0. Right here. Next one, 5/3, negative 4. So that's not quite 2. At 2 or at negative 8, so something like this. So as you can imagine, your curve would look probably something like this. So your original function is going this way. Your transform function is going down this way. Why is it going down? It's because your a value is negative. So that's why the entire thing shifted upside down. Okay? Let's do, what else is the question asking us? It's asking us, state the impacts of the transformation on the domain. Okay, cool. So what's the domain of an exponential function? By the way, this curve, I don't think I drew the direction properly. So remember, every exponential function has what? It has an asymptote. So the original function, the one in red, the asymptote, this is the parent function. The asymptote is the x-axis. For our transform function, this guy, where's the asymptote? Remember, the asymptote is always the c value, the vertical stretch value. Not the vertical stretch, but rather the vertical translation. So here, I didn't quite draw this properly. There should be an asymptote at positive 4. So technically this graph should be drawn. I drew it wrong here. Let me just fix this. So the fix is this. There's an asymptote at positive 4. So let's say this is the asymptote at positive 4. Our curve had a point here. So it should have looked like this. Comes from negative 4 and then goes through our points. We had a point here, we had a point here, like that. And that makes better sense. Every exponential function must have an asymptote. So now let's talk about the domain and the range. First, let me kill this question by writing the equation. Once you see the equation, everything is very easy. The equation, in a sense, is already given here, but you need to know how to convert this into this form. So look at this, the equation here. The a value never changes. A is always gonna be outside the function. So with no fear, you can just write -2 times. Now your function in this case is your exponential function. So it's 2 power. And power, we have k, so 3x minus d plus c. There we go. That is the equation for this transformed exponential. So now what we're going to do is we're going to comment on the domain and the range. So let me make a table here. So we can say this is for 2 power x, and let's say this is for f of x, the transformed function. What's the domain of an exponential function?
It's XCR.
It's x here, exactly. So did the transform function, is that going to change the domain? No, it's not. The domain of an exponential function is always XCR. Okay, now let's talk about the range. What's the range of 2 power x?
Y has to be greater than 0.
Exactly, perfect. What's the range for this function? And again, remember what the asymptote is.
Y has to be greater than 4.
Greater than or less than?
Less than.
Less than 4. Because it's gone down because of this -2, it's going down. Okay, the next thing, what do they want? Intervals of increase. All right, so this one's pretty easy to see. If you look at the parent function, the one in red, it's increasing everywhere. And it's decreasing nowhere. Whereas the transform function, the one in blue, this guy right here, it's decreasing everywhere. It's increasing nowhere, right? But it's going down the whole time. And lastly, we have end behaviors. Okay, so let me just comment down here. This is the original function. This is the transform function. There's an asymptote here at 4 for the transform function. For the original function, there's an asymptote here. All right, now let's talk about end behaviors. We're going to do this for the parent function, and then we're going to do this for the transform function. As x goes to positive infinity, for the original function, where's y going? For the red function.
It's also positive.
It's also positive. Whereas when x is going to negative infinity, where's y going? On the other side for the red function.
It's negative.
Negative what?
Negative infinity.
No, it's not. So again, what's the question? The question is for the red function for 2 power x, as x goes to negative infinity, right? You see, let's say this is negative infinity on the x. What's the y value here? Is that negative infinity? On the y-axis? No, right? It's 0. As x goes to negative infinity, y goes to 0. Now let's look at it for the transform function. As x goes to positive infinity for the green function, where does y go?
Negative.
Yes. As x goes to negative infinity on the green function, where does y go?
To 4.
4. Perfect. And that's the answer to this question. Okay? You see why it's not negative infinity here and here? Because it'll never cross that line, right? It's not allowed to cross that line. Therefore, that's going to be the y value that it approaches. It'll never get there, by the way. when we say this approaches means it'll never get there. It's gonna try and get there. It'll get to 0.00001, but it'll never get to exactly 0. So that was a good question. Okay, here's another question. This one doesn't require a sketch. Okay, we have a function is on the graph of this one. So we have a point, we have a transform point. The question is asking us what were the original points. So we don't know what kind of function this is, but there was a point here on the original function, which has now moved. There's no transformation, but it's gone down a bit. So that point has now moved here. The question is telling us after it's moved, the point is 3, 6. Okay, after moving it, what was the original point to begin with? That's the question. Any ideas on how to solve this? You don't have to sketch this to solve this. In fact, we don't know what the sketch looks like because we don't know what f is. So it's not a graphical solution kind of question.
Do we use the point mapping?
Yeah, we use the point mapping rule. So what does the point mapping rule say? It says any point xy on the original curve transforms to x over k plus d, right? ay plus c. You see these points? Are these xy's or are these x over k plus d, ay plus c's? What are those? Original points or transformed points?
They're transformed.
They're transformed. So that's not x, okay? So that is this. So check this out. X over k plus d is actually 3. Ay plus c is actually 6. After we've transformed them, that's the points we got. Now what do we do? What do you think we do? We need to solve for x and y. And again, it's easier than it looks. We know what a is. A is 2. What's k?
1,
1. What's d?
-1.
Yeah, and c is -4. So now let's just put all of these in. So we have x over k, which is just 1. So x over 1 is just x minus d. So -1 is equals to 3. And on this side, we have 2y minus c is -4 is equals to 6. And look at this. Now it's easy. X is 4 and y, it's a terrible y. Y is 10 over 2. It's 5. Final answer. And you are done. That makes sense?
Uh-huh.
So again, most of the anything with transformation, it's ultimately it comes down to point mapping rule. Yeah, let's see what else we can do for the last few minutes. Okay. Let's try this one. We're given this function, y is equals to negative root x plus 2. It's a root function. What we're gonna do with this is we are gonna sketch the inverse. Okay, that's the question. Sketch the inverse of this function. Do you remember what an inverse is? What's an inverse? Inverse is, well, something graphically. I think this is the easiest way to explain it. Inverse is something that is reflected on this line, y equals x. For example, you have a function 2 power x, you shift it on this line, you get log of x. That's an example of an inverse. Another example is if you have a quadratic like this, the inverse of a quadratic is this weird looking function. It looks like this. Ultimately, what it is a reflection on the line y equals x of the entire function. From a table, it's when x becomes y and y becomes x. For example, if you have x, y, 0, 1, 2, 3, the inverse of that is 1, 0, 3, 2. Just literally flip all the x and y values from a table. Another approach to inverses is doing it algebraically. That is when x becomes y and y becomes x, and then you solve for the new y. We've done this before, but let me show you. We're given a root function. The question is now asking us to sketch the inverse of this function. There's multiple ways to do it. Let me do it in a way where I first find the equation. So what I'm going to do here is I'm going to find the equation for y inverse, and then we're going to sketch y inverse. So how do you find the inverse from an equation? So we're given this equation, y is equals to negative root x plus 2. So to find the inverse, algebraically, what you do, step number 1, is you swap x and y. X becomes y, y becomes x. This is called interchanging the variables. Once you do this, the next step is you solve for the new y. It's actually not that difficult. Look at this. So y is now x is equals to negative is negative, and now we have a y in here, like that. Now we need to isolate, we need to solve for this y. How do we solve for that y? We need to get rid of the root, we need to get rid of the plus 2. How do we solve for y in this equation? Well, let's first get rid of the minus sign and the root. What I'm going to do is I'm going to square both sides. So on the left, we get x squared. On the right, negative sign squared is positive, so it disappears. Root squared, root disappears. So just left with y plus 2, like that. And then finally, subtract 2 from both sides. So there you go, that's the inverse. So now, what was the question? The question was sketch the inverse. We could probably sketch both in the same plane. So x squared minus 2, what does that look like? There is a intercept at minus 2. And then these will be at 1 point something. The x-intercepts would be at 1 point something. So there you go. That is the graph of the inverse quadratic. What we can do is we can also sketch this. So this one is negative x plus 2. So root x looks like this. It shifts upside down because of the minus sign, and then it goes 2 units to the left. So it kind of looks like, maybe kind of looks like this. So that's the square root function. And we have both of them on the same plane. That's how you sketch the inverse of a function. Did that make sense?
Mm-hmm.
So one thing to note here is that this is not perfectly to scale, but notice how the square root function, we only have one chunk coming out of it, right? We only have one line coming out of it. But the quadratic, we have two lines coming out of that node. What that means is basically square root function, your x has to be, at least the parent function, your x has to be greater than 0. So you'll never get a double-sided root function. You'll only get one side at a time because it's restricted by its domain. But a quadratic, the domain is XCR. So it's not restricted. That's why it has like two chunks here compared to the one chunk of the square root. All right, let's call it there for today. From here, we'll just meet using this link. Okay?
Okay, thank you.
See ya.